Good evening, Internet. I am Matt Buyak, and in this video we will take a look at the 34th problem from the Project Euler problem archive. So this problem asks a question about the sum of the factorial of digits of positive integers, and in particular to find numbers for which that sum gives us back the number itself. For example, 145 here, if we take 1 factorial plus 4 factorial plus 5 factorial, we get back the number 145. And it asks us to find the sum of all such numbers with at least 2 digits. Now I find that often Project Euler problems will fall into one of 3 categories. You've got the computer science problems, which ask you to use some technique from classical computer science to solve the problem. There are the number theory problems, which require finding some clever mathematical pattern in the problem in order to solve them. Even if you might end up solving them by writing code, there's still a mathematical element to them. And then there are the fake number theory problems, which seem like maybe number theory is applicable, but in reality, the only option you have is to brute force the problem. Though I will concede that the difference between a real number theory problem and a fake number theory problem may just be a matter of the cleverness of the solver. I would consider this to be a fake number theory problem. And so we will be using brute force in order to solve it. Now, one thing you may note is that they didn't ask us to find, as some of these problems do, all solutions less than 1 million or 10 million. They asked us to find all solutions. And so that indicates that there's some upper bound that we haven't been given and will have to determine ourselves. So with all of that out of the way, let's get into it. Let's open up a shell and copy our template directory to make our problem directory. And we will open up our analysis file. So I want to introduce 2 functions. We'll call them f and g. And f is going to be, we'll say f is the smallest possible positive integer with d digits. And then g is going to be the largest possible sum of factorial of d digits. And you'll notice that if we can show that beyond a certain point f grows larger than g, then we know that we will have no solutions beyond that point. That is, any number you pick beyond that point will produce a sum of factorial of digits that is smaller because g is smaller than f. So we'll note that f of d is just going to be equal to 10 to the d minus 1. And g is just going to be equal to d times 9 factorial. That is, if every digit in our number is a 9, then the largest possible sum of factorials of digits is going to be d times 9 factorial. And I hope it's not too difficult to see that as we increase the value of d, f is going to grow by factors of 10, but g is just going to grow by a constant amount. Now that constant is actually fairly large. If we just pull up our calculator here, take a look at 9 factorial, is 362,880, so fairly large. But eventually f is going to grow large enough to surpass g. Now we could do some further analysis to determine when that might occur, but we can actually come up with an answer just by trying a few possibilities. We'll notice that 9 factorial is itself a 6-digit number, so obviously we don't have to consider whether or not there are any values of, or whether the point at which f crosses g is at d equals 6. We know that it's some point beyond there. So let's consider d equals 7. So we'll notice that 10 to the 7 minus 1, you really don't even need a calculator to figure this out, is going to be 1 million. The smallest positive integer with 7 digits is 1 million. And if we do 9 factorial times 7, that gives us 2.5 million. And so you can see that it is in fact possible to get 7-digit numbers by taking the sum of factorials of the digits for 7 digits. So now let's consider d equals 8. I hope you can see that f of 8 is going to be 10 million. And then we'll compute g of 8 is only 2.9 million. And so we can see that for d equals 8, f has surpassed g. And so that means that there will be no solutions with 8 digits or more. So let's go back to that value of g of 7. So that was 7 times 9 factorial, 2.5 million roughly. This is going to be our upper bound. We could actually tighten it up a little bit if we had to, but we really don't need to. My usual rule of thumb for a brute force approach is that if you can keep your search space under 10 million, that's going to be good enough. So let's get to writing some code. Open up our main.cpp. And I'm just going to hard code the factorials here. It's going to be, you'll note that 0 factorial is 1. I believe this is by convention, but it is a very useful convention. There are certain theorems that are much better behaved if we have 0 factorial being equal to 1 rather than some other value. Okay, so 0 factorial is 1. Then we have 1, 2, 6, 24, 120, 720, 50, 40. And at this point, I have to pull up the calculator because I don't have the rest of them memorized. So we have 40,320. And 362,880. Obviously, we could just calculate this in our code, but there's a small enough number of them, we can just hard code them. That's fine. Okay, so let's now write a little function here, is solution. And this is just going to take our integer n and calculate the sum of the factorial of its digits. So we'll need to be able to convert this to a string. Not strictly required, but it's probably the easiest way of getting the digits out of a number. So we'll say string nstr is equal to std to string n. Then we'll need, actually we can make this const. Need a variable to keep track of our sum. And then we'll just say for each character in the string, we're going to add ch minus 0. So this is just converting from characters representing digits to the integer value. This minus 0. This is the 0 character. Oh, excuse me. I'm going to have to take the factorial of that. And I'm just going to make a quick comment here. This is technically a bit unsafe because we're indexing into this finite array after doing basically assuming that this is a digit. If this isn't a digit and it's some other character, then this can end up indexing outside the array, and it is potentially the makings of some kind of exploit. But this is just a harmless little programming puzzle, so we will leave it at that. And we'll just return sum is equal to n. Let's see, so we'll say const uint 32t upper is going to be equal to 7 times factorial 9. And we're just going to increment over, excuse me, we want to be careful. The problem specifically said not to consider single digit integers, and so we want to start at 10. As before, initialize our sum to 0. And we'll say if is solution n sum plus equals n. And it's probably useful actually for us just to print out the solutions that we find so that we can do a sanity check. Obviously, we expect to find 145 among the solutions, and so we want to be sure that that is in fact the case. And then down here, we'll just say sum is equal to sum. Oh, haha, see, this is an example of why you make your constant variables constant, because then it will help you catch stupid mistakes like this when you try to modify a constant variable because you paying inadequate attention to what you were doing. Okay, so we have an answer here, 40,730. So we can go to the archive and check to see if that is correct. Except I appear to be signed out. I'll just move this over here for a moment while I enter in my password. And there we are. There is our answer, 40,730 as expected. So thank you for joining me for that video. In the next video, we will tackle problem number 34.